Okay, so I'll talk about the SEIRIOS mission. This is the mission collaborate with Matsuo Sensei. And first of all, I introduce myself. So I'm Satoshi Ikari, and now I'm associate professor of the ISSL Intelligent Space Systems Laboratory in the University of Tokyo. And sorry. So yeah, Intelligent Space Systems Laboratory is the Professor Nakasuka's laboratory. Maybe everybody knows him. And yeah, we already developed about the 16 micro and nano satellites mission. And now we are focusing on developing the new project named SEIRIOS. So, yeah, I'll talk about the background of SEIRIOS. And SEIRIOS is the formation flying demonstration mission. So, I'll first introduce what is the formation flying. And the formation flying is a mission architecture in which multiple spacecraft measure and/or control their relative position and attitude to accomplish objective that cannot be achieved by a single spacecraft. So as you know, the single spacecraft has a very has a limitation like size constraints imposed by the launch vehicle fairing or mission risk in the event of a single point failure. So the formation flying satellites can yeah, overcome the especially the size constraints because we can use the multiple satellite to make the very large baseline or baseline like life like mission mentioned by Professor Matsuo. And one important point is formation flank is not same with the constellation. The constellation is also very important technology using a multiple spacecraft. But the constellation, usually the satellite relative distance is very long, like the several 100 kilometer or 1,000 kilometer, and each satellite operates independently, not cooperate on the orbit. And the cooperation occurs at the higher layer, like the data or mission layer. So it's the difference between the constellation and formation flying. Yeah, anyway, I focus on the formation flying satellite mission to realize the interesting science mission like infrared interferometer. And yeah, this is the overview of the multiple satellite mission. And the vertical axis shows the control accuracy requirement, and the horizontal one is the intersatellite distance. And yeah, you can see the very long intersatellite distance and rough accuracy. There is a constellation, and very short intersatellite distance and high accuracy. There is a rendezvous and docking technology. Sorry, it's in Japanese, but yeah, and usually the formation flag mission is the medium intersatellite distance and medium accuracy requirement. But recently, to realize the interesting science mission like X-ray telescope or infrared interferometer or the gravitational wave antenna, uh, yeah, the many scientists requires high precision formation flying. So we need to yeah achieve the more accurate formation flying control, like the 1 micrometer or less than 1 millimeter in the satellite intersatellite distance around 100 meter to uh, yeah 10 kilometer or something, and the in the space infrared interferometers, already Matsuo Sensei talked about this. The the high resolution infrared observation requires long baseline as space interferometry, like the 100-meter baseline is necessary. And but the several formation flying infrared space interferometer concepts have been proposed, but it was unfortunately these mission plans were stopped, cancelled. because there are several key challenges. The one is the cost, the development and launch cost of the multiple large spacecraft is very high. And another one is the technical risk and the achievement micrometer level, relative position, and attitude control accuracy is very, very difficult. So combination of this high cost and high risk, yeah, the most of the formation flying space interferometer mission is canceled. So we considered how to yeah, overcome these high cost and high risk problem and to realize the formation flying infrared space interferometer. The one is the reduce the cost by the utilizing microsatellites, and this is our strong point, the ISS's strong point, because we developed a lot of microsatellites, and recently our microsatellites, yeah, reached to the high attitude control accuracy, and also our spacecraft reached to the good maneuverability using the micro thrusters. And the second key point is the relaxation of the requirement for the control accuracy from micrometer level to millimeter level by employing the densified pupil spectroscopy interferometer. This densified pupil spectroscopy interferometer is proposed by Professor Matsuo to relax the control requirement for the infrared interferometer. So combining these two approach, the requirement relaxation and cost reduction by using microsatellite, and we proposed the SEIRIOS mission, the space experiment of IR interferometric observation satellites. And we proposed this mission to the Japan's Space Strategy Fund, yeah, theme of the high precision satellite formation technology. And our proposal was selected as one of the this very big funding around 15 million dollars, yeah, funding. And this is an overview of our proposal. We have the three very important activities. The one is the development of SEIRIOS project using the microsatellite, two 10 kilogram satellite and 150 kilogram satellite. And we want to demonstrate the world first space interferometer. Second activity is the test development of the test equipments. So to realize the SEIRIOS mission, we need to yeah, test the formation flying technology on ground. So development of such kind of the infrastructure for test is another very important activity. And the final activity is the making the community to use the future accurate formation flying mission. So I'll talk about the SEIRIOS mission. Okay, the SEIRIOS is, yeah, again, the space infrared interferometer with densified pupil spectroscopy by 3 micro and nano satellites. And our target wavelength is around 0.7 to 1 micrometer, and the current aperture diameter is 8.5 centimeter. And this is the, yeah, docking form of the SEIRIOS, and this is the formation flying form of SEIRIOS. That's firstly the, yeah, SEIRIOS is mounted on the launcher, the rocket, as a docking form, like a single microsatellite. And after that, the two CubeSats, 10 kilograms CubeSats, deployed from the mother satellite and making the formation flying, yeah, architecture. And the right figure shows the optical diagram of this interferometer. The yeah, the light from the celestial body coming from up, and the two CubeSats mounting the, how can I say, mirror angle with the 45 angles, and the lights are reflected to the mother satellite, and to light reflected from the two CubeSats combined inside the mother satellite, and uh, we can take the interferometric fringe in the mother satellite. So yeah, to realize that the mother satellite always in the center of the two CubeSats, and the yeah baseline it will be the intersatellite distance between two CubeSats, and our target baseline will be the 10 meter to 100 meter on orbit. So, and one of the key technology to realize this SEIRIOS is this one, the DPSI, densified pupil spectroscopy interferometer. And yeah, this technology, I cannot yeah, explain deeply this technology today, but yeah, this interferometer is the usually, sorry, the so one yeah, important point of this interferometer is two reflected beams are combined at the pupil plane, not at the focal plane. So you normal interferometer is yeah, two beams are combined at the focal plane, but this interferometer uses the pupil plane, and thanks to the using the pupil plane, the requirement, the control requirement for the attitude is relaxed. And also, this interferometer works as the spectroscopy, and thanks to the spectroscopy, the coherence length is extended, and because of that, the relative control position, sorry, relative position control accuracy is relaxed. And yeah, sorry, I skip. And thanks to the using the yeah DPSI, the relative position accuracy and relative attitude accuracy requirement both are relaxed from the yeah conventional 1 micrometer order to 1 millimeter order, or the 1 microradian order to 100 microradian order. So yeah, around this control requirement, maybe the microsatellite can achieve, can satisfy these requirements. So that's why we started this mission together with Matsuo Sensei. Yeah, and this is a serious mission definition. The yeah the main mission is a high pressure formation flying technology demonstration with microsatellites, and our target launch date is in the 2031. And the mission objective, the first mission objective is engineering objective, and it's establish sub-millimeter level precise formation flying control. It means the demonstrate of the real-time onboard formation flying with three satellites over a wide separation range from meter to sub-meters. And the science objective is the achieving the on-orbit measurement of infrared interference fringe with DPSI. And yeah, ultimately reconstruct image like this by acquiring multiple interferometric fringe to fill the UV frame. Okay, and yeah, one important point is yeah, sorry. So this is not a direct imaging of exoplanet. The direct imaging of exoplanet will be the future future mission, but the SEIRIOS will be the first step to realize the formation flying interferometer like live mission. Yeah, explained in the Matsuo Sensei. Yeah, and this one is the yeah yeah, observation of SEIRIOS. Yeah, so one the normal observation of the SEIRIOS is this the middle figure. It's the observed fringe taken by the SEIRIOS, and usually this fringe, maybe everybody can not imagine what is this observed fringe, but if we can get this fringe on orbit, maybe 100 fringes or the 1,000 fringes with the multiple baseline lengths or multiple how can I say, the relative geometry with respect to the target body, we can get this kind of the reconstructed image with the on-ground image analysis. And this example shows the if when we get the observed fringe from low Earth orbit, the observed fringe of the Europa from low Earth orbit, and we can reconstruct that this kind of the very high resolution Europa image from low Earth orbit, not directly go to the Europa using the deep space spacecraft. Yeah, and yeah, this is the overview of SEIRIOS bus system. The mother satellite is a microsatellite like the 50 kilogram, and the two daughter satellites are CubeSat size. And as you know, the Intelligent Space Laboratory, the University of Tokyo, already demonstrated the 50 kilogram microsatellite bus using Hodoyoshi 3 and 4 and the CubeSat bus using Ikari. So we already have the base technology of these two satellites. And to realize the formation flying control, we just need to add this kind of the formation flying sensors and actuators like CD-GPS, it's a carrier phase differential GPS, or inter-satellite link, or optical navigation system, or radar distance meter. And we also use the fringe image for the image feedback to realize the most accurate control. And for the actuator, all three satellites amounts to thrusters and yeah, to the chip mirror or delay line, like it's the more accurate control of the optics will be installed. And this is yeah, overview of the orbit design. The reference orbit that is the 600 to 800 kilometer dawn-dusk orbit, and the relative orbit is like this. So if the target sets the body on the same direction with the orbital plane, yeah, the formation will be the perfect along track formation. But if the target stress body is a little bit inclined from the orbital plane, yeah, we just need the make the inclined relative orbit for the two CubeSat like this. And I can skip this, but yeah, we already calculated the orbit maneuver to control the baseline length or to control the target celestial body direction using with the very small data B. Yeah. And yeah, this is the overview of the SEIRIOS spacecraft itself. But as I already said, the making or developing the ground experiment equipment is also important activities for our project. The first one is the development of the 6 degree of freedom thrust stand. Thrust stand means the measuring that thrust or torque generated by the thrusters mounted on the spacecraft. And this is the research of the Koizumi sensei in the University of Tokyo, and they developed this kind of the 6 degree of freedom thrust stand with the 1 micronewton accuracy. And to measure the characteristics of the torque or thrust of thrusters, and we can achieve the more accurate formation flying control. Another yeah, equipment is the GNSS signal simulator. As you know, the relative navigation with GNSS receiver is essential for accurate formation flying mission. So we developed the hardware in the loop simulator, including the GNSS real RF signal simulators. Yeah, and this last one is this air bearing table. The air bearing table realized the 3 degrees of freedom relative motion with the frictionless table. And using these two frictionless table, the one satellite moving on this table and other one moving on this table, and we can demonstrate the formation flying control on ground using this air bearing table. Last one is this ground experiment for DPSI. Yeah, collaborative with Matsuo Sensei, we already demonstrated the concept of DPSI on our yeah on the ground, and this is the ground experiment for the PSI, and we already got the interferometric fringe like this, and this fringe is very yeah compatible with the observation simulator like this. So finally, I summarize my presentation. Yeah, we proposed the SEIRIOS mission, Accurate Formation Flying Demonstration Project, and it was selected as R&D theme of the Space Strategy Fund. And we will develop SEIRIOS satellite and testing equipment. And the sales will be launched in the fiscal year of 2030. Okay, that's all. Yeah, thank you for your attention.